So we've defined matrix multiplication so that it corresponds to composition of linear transformations, but this definition is kind of a little eye-watering. It's a little hard to wrap your mind around exactly how this works without looking at some examples of actually computing matrix products. So let's do that. What we'll see is that this is actually a familiar operation. It's just that operation done more than once. So the thing to notice is that if we take this column, right, so to compute this entry, the ijth entry of the product, we take the ith row, the jth column, and if we turn this column sideways and sort of spread it out above the matrix on the left, if we swipe downwards when we get to the ith row and do our usual vector matrix thing, we get exactly this result, right? AI1, B1J plus all the way down to A1R, BRJ. So that's exactly this sum. So this is essentially exactly the matrix vector product, but just with each column from the right-hand matrix individually. So with that in mind, let's work out some examples. So for this matrix A and this matrix B, let's calculate B times A and also A times B. So for B times A, I'm actually going to write out B and A again. So this is 6 minus 1, 1, 3 times 2, 1, 0, 3 minus 5, 2. Okay, and so how you do this is so to get the first row, first column entry here, we take the first column here and the first row there, right? Turn this column sideways, 2, 0, 5, and then swipe downwards, right? And do our usual multiply and add. Well, you see there's a problem here. This matrix on the left, B, it doesn't have enough entries in its row to sort of multiply with each one of these. So what that means is that the sizes here, the sizes of these matrices just aren't compatible. So this matrix product actually doesn't exist. So this is undefined. And this makes sense for a couple reasons. So first of all, we multiplied, when we first defined what we meant by matrix multiplication, we had an m by n matrix, we multiplied that by a p by n matrix, and what we got was a p by n matrix. So what happens to the sizes is, first of all, the inside sizes have to match, and then they sort of get used up when you do the product because of the summing that you do. And so the remaining sizes are p and n, and so you get a p by n. Well, these sizes are 2 by 2 and 3 by 2. These inside sizes don't match. So that means that this matrix product is undefined. Another reason that it should be clear why this is undefined is because if you think about this in terms of linear transformations, a vector what would this represent as a linear transformation? Remember, matrices represent linear transformations by matrix vector product, so you'd multiply by a vector, you'd put a vector over on the right here to do a linear map. So you'd have to start with a vector in R2, because you have to have the same number of entries in the vector here as you do columns over here. So you'd start in R2. Multiplying by A would give you something in R3, right? Because the number of rows in your matrix is going to be the number of entries after you do a matrix vector product. And can you use the matrix B to get from R3 to some of the other Euclidean space? Well, no. B is 2 by 2. Using B to represent a linear map, your linear map would have to start in R2, not R3. So this product doesn't make any sense because the domain, the codomain of one doesn't match up with the domain of the other. Notice that, again, this product, BA, is backwards compared to this diagram. That is to be expected because the order of the matrices matches the order of the functions as you write them down, like, right, this. So B of a vector, right? So the order of the matrices matches this way of writing functions, not this diagram way of writing functions. So got to be careful. Okay, so what about the other product, A times B? Well, if we do A times B, again, A is 3/2, B is 2/2, and so this time the inside sizes do match, and the result will be the outside sizes, 3/2. So this product will be defined. So with that in mind, let's go ahead and work it out. So 2, 0, minus 5, 1, 3, 2. And we're going to multiply by 6 minus 1, 1, 3. Okay, so what do we get? So first let's work with this first column. And remember, the column that you use from the matrix on the right tells you what column you're filling in the product matrix. So we're going to be working out this first column. So turn it sideways over our matrix. And then, just like with the matrix vector product, sweep downwards doing your multiplication and adding thing. So the first entry here is going to be using the first row there. So 6 times 2 is 12, plus 1 is 13. And now we move down a row. The second row here will be this, give us the second entry there. We're still using this same first column, though, because we're still in the first column of the product. So 6 times 0 plus 1 times 3, that's 3. And then last row gives us the last entry. 6 times minus 5, minus 30, plus 2, negative 28. Okay, now we're done with this first column, so stop using the first column. Now we're going to do the second column of the product, so use the second column from the matrix on the right. Take that column, tip it sideways over the matrix, and then sweep downwards. So first row from the matrix on the left gives us the first entry in this column. So minus 2 plus 3 is 1. And then sweep downwards. So minus 1 times 0 is 0, plus 9. And then 5 plus 6, 11. So there's our matrix product. Okay. So on the one hand, this is a good example of actually working out matrix multiplication. On the other hand, this demonstrates, very starkly that this matrix multiplication operation that we've defined, it's not commutative. It can't be commutative because A times B is this matrix. B times A isn't even defined. So matrix multiplication is not commutative. That makes sense when you think of matrices as representing functions because, for a function, is G composed, if F composed with G equal to G composed with F? Well, not usually, almost never, in fact. So it makes perfect sense that since the composition operation on functions does not commute, the matrix multiplication operation shouldn't commute either because matrix multiplication represents composition of linear maps. Okay, let's look at another example of computing a matrix product. So this one is much bigger, but what I want to show you with this example is that even though it's pretty big, as long as the individual numbers aren't that messy, you can actually do this sort of all in place, all in one step, without having to write out a ton of extra work. Of course, you have to do that work in your head, but at least you don't have to write it out. Just to see what the sizes are going to be, this one's 3/3, this one's 3/4, so this matrix product is defined because the inside sizes match, and so the product will be the 4/3, or sorry, no, 3/4, the outside sizes, right? Okay, so what are we going to get? So first take 1, 0, 4 and turn them sideways, right? I'll write them down, but usually if I'm working out a matrix product, I don't actually write them here. I just sort of visually or imagine moving them up and sideways like this. 1 times 3 is 3, plus 0, plus negative 4, so minus 1. And then slide this downwards. 4 plus 0 plus 16, so 20. And then on the last one, 0, 0, minus 8. So there's our first column. Now we move over to the next column. Do the whole thing again. So minus 6, minus 2 is minus 8, plus 0, so minus 8. And then minus 8 plus 6 is minus 2, plus 0, so minus 2. And then 0 plus 1, 0, so 1. Okay, third column, 3 plus 6 is 9, plus another 2 is 11. 4 minus 18, so negative 14, minus another 8 is minus 22. I feel like I messed up. 4, positive 4, minus 18, minus 14, right? Yes. Plus another 8. Okay, no, that's, or minus another 8. Yeah, that's right. I hope. Okay, and then, so last row, 0, minus 3, plus 4. That one's 1. That one I can do. Last column, 0, 1 times 3 is 3, plus 10, 13. Oops, I'm sorry. That was, for some reason, I jumped down to the last row there. Okay, so first row, 0, 0, 5. And then 0, 18, minus 20, so minus 2. And then just to check, 0, 3, and 10, yeah, 13. So there's our matrix product, right? I had to do all that arithmetic. There's no way of getting around doing the arithmetic, but if you're organized, you can do it all in your head and you don't have to write out pages and pages of calculation just to do one single matrix product. One last thing I want to mention about just the mechanics of working out a matrix product is this. So imagine organizing your matrix product this way, writing B as, so let's write A in terms of its columns, or sorry, A in terms of its rows, so rows A1 down to AM, and you know what, let me change the size of these so that they match the way that I've been doing it. So this was P times M, this was M times N. That's the way we had it, and so this should go up to B sub N. Okay, so A, let's write A in terms of its rows, so A row A1 down to row A sub P. So what would this matrix product AB look like? Well, remember that AB, the matrix on the left, you're going to use the rows of anyway. And the matrix on the right, you're going to use the columns of anyway. So when you multiply these matrices in the ith row and the jth column, what you get is just the dot product of the ith row from A and the jth column from B. So that's one nice way to think about what this matrix product is doing. You're actually just computing dot products for all combinations of rows and columns. There's another way to think about what's going on here. Notice that if we worked just with the first column of this matrix, of the first column of B, what we would do is sort of turn it sideways over the matrix A and then swipe it downwards. But that is exactly how we computed a matrix vector product. So the first column of the product is actually just the matrix A, matrix vector product with the first column of B, and so on. The last column of the product is the entire matrix A, matrix vector product with the last column of B. So interpreting it this way gives you another perspective on what the matrix product is doing. And in fact, what this is yet another way to interpret what this is saying is that each column of the product is just a linear combination of the columns of A using coefficients from B, right? And that we actually maybe see over here.